Okay, these are the solutions to question number 6 from the 2015 examination paper. 6 part A, we're looking at subspaces of vector spaces. Part B is just bookwork, so we want to prove that the image of T is a subspace of V. And for part C, we want to find the coordinates of a vector, this vector here, relative to this basis. So for 6 part A, we want to determine whether W1 or W2 are subspaces of P3 over R. Now normally, not always, but normally one of these is a subspace and one of them is not a subspace. Now for W1 here, we have modulus. You can see you've got modulus terms, and straight away we can see that this is not going to be a subspace. So if we look at 6a part 1, then we can show that W1 is certainly not empty because the vector 0.1 plus 0.1x cubed is in W1. Okay, because the modulus of A0 is 0.1, the modulus of A1 is 0, the modulus of A2 is 0, and the modulus of A3 is 0.1. So the modulus of A0 plus modulus of A1 plus modulus of A2 plus modulus of A3 in this case is equal to 0.2, which is certainly less than 1. So this vector does belong to W1. However, the vector 10 times u, so this is 10 times u, would give us the vector 1 plus x cubed. You can see that 1 plus x cubed does no longer satisfy this expression here. So 1 plus x cubed is not in W1. So therefore W1 is not a subspace of P3 over R. Now W2 is equal to polynomials, is a subset of polynomials such that A0 plus A1 is the same as A2 plus A3. So we can certainly show it's non-empty because the vector 1 plus x squared plus x cubed is in W2 because A0 plus A1 is 2 and A2 plus A3 is also 2. So this vector certainly belongs to W2, showing that it is non-empty. Then we take two general vectors, u and v, which belong to W2. So that means that A0 plus A1 is equal to A2 plus A3, and B0 plus B1 is equal to B2 plus B3. So the vector alpha u plus v is equal to this expression. We can collect constant terms, x squared terms, x cubed terms, etc. And then using the fact that A0 plus A1 is the same as A2 plus A3, etc., then we can show that alpha A0 plus B0 plus alpha A1 plus B1 is certainly then the same as alpha A2 plus A3 plus B2 plus B3. So that proves that W2 is a subspace of P3 over R. For part B, as I said, this is just bookwork. So the image is non-empty because T of 0 is in the image. If V and V dashed are in the image and alpha belongs to the field, then V has to equal T of U for some U belonging to the vector space capital U, and V dashed has to equal TU of dashed for some U dashed belonging to U. And then if we write down alpha V plus V dashed, we want to prove now that alpha V plus V dashed is also in the image. Well, alpha V plus V dashed is equal to alpha. We've just said that V has to equal to T of U, V dashed has to equal to T of U dashed, and now because T is a linear transformation, that has to equal T of alpha U plus U dashed. So therefore, alpha V plus V dashed has to be in the image, and the image is a subspace of V. And finally, we want to find the coordinates of this vector with respect to these bases. So we just want the coefficients. We're looking for coefficients A, B, and C. So we just equate this. So for example, on the left-hand side here, we have a constant, -2, and that should equal the constant on the right-hand side, which in this case you can see is B plus C. So we have B plus C is -2. Then if we look at the coefficient of x, we have 7 is equal to A minus B. So A minus B is 7. If you look at the coefficients of x squared, 3 is equal to A, so A is 3. And if you look at coefficients of x cubed, 2 is equal to C. So we find C and A, so then it's easy to find B. So there's the expressions for A, B, C. And remember, we always express the coordinates in square brackets. Okay, so we express coordinates in square brackets. So that concludes the solutions for question number